Welcome back, Stu Murphy here. In my previous video, I developed a process for taking a regular polynomial, third degree, and turning it into an equivalent Taylor series polynomial by repeatedly taking the derivative of the regular polynomial up to and including the third degree. In this video, we're going to do something very similar, but instead of creating equivalent polynomial, we're going to create a Taylor series approximating a polynomial. Let me remind you, first of all, what polynomial was we used in the last video. So we had f of x equals 4 plus 2x minus 3x squared plus 6x cubed. And repeatedly taking the derivative of both sides of this f of x polynomial plus a Taylor series generalized format of the polynomial, we got the resulting p of x. And by the way, this was centered at 1. You can center them at 0, which is called the Maclaurin series, or at other values, but to keep the numbers simple, we centered it at 1, and the resulting polynomial was 9 plus 14 times x minus 1, and that 1 represents where we center the polynomial around. Let's see, plus 30 over 2 factorial times x minus 1 squared. And the reason we have this squared is where the Taylor series has increasing powers. It's a power series. And finally, plus 36 over 3 factorial times x minus 1 cubed. Now, to make a little bit more room, let me erase what I wrote here, just to make some more room. I already mentioned that it's centered at 1. Hopefully that does the trick. And to complete the format, so you can see that the increasing degree also results in an increasing factorial underneath. The 9 we could say is under 0 factorial, which equals 1. And the 14 under 1 factorial, which also equals 1. And so if we had, for example, an x minus 1 to the 4th, it would have been multiplied by the 4th derivative of f of x, and would have been over 4 factorial. So let's just identify. Let me pick a new color. We'll do red here, I think at this point. This 9 represented f of x at 1. This 14 represented f prime of x at 1. This 30 represented f double prime of x at 1. And this 36 represented f triple prime, triple derivative, third derivative, x at 1. We're going to do the same thing here with our Taylor series polynomial, but now we're going to set up an approximation rather than simply always an equivalency. So the only time for difficult functions such as the square root of x, and we're going to approximate the square root of 3. That's a difficult function. It goes to infinity. It perfects at infinity. Anything less than infinity, the square root of 3 becomes an approximation. And the way we can approximate that is with the Taylor series polynomial. So we're going to follow the same process of taking repeat derivatives. So let's begin with our straightforward f of x, which equals, well, we can't use square root of 3 because I don't know what the square root of 3 is. So what we're actually going to do is we're going to center this at, center at square root of 4, because we know the square root of 4 equals 2, and it's pretty straightforward. So f of x, not surprisingly, if I convert square root of x, if I use the notation, fractional notation, replace that with 4, and we know that equals 2. First derivative, f prime of x bring down the 1/2, and we subtract 1 from the exponent, so now this becomes negative 1/2. We plug in 4, and it simplifies, plug in 4, and it simplifies to 1/4. Now let me just continue to list these. So we'll repeatedly take the derivative. We would bring the negative 1/2 down. This would become negative 3/2 as the new exponent. Negative 1/2 times 1/2 is negative 1/4, and then we plug in 4. So for our second derivative, we would get f double prime of x equals negative 1/32. Third derivative, f triple prime of x at 4. All right, plug in our 4. Remember, we're plugging in 4 each time. That equals 3/256 positive. 256. And fourth derivative of x at 4 equals negative 15/2048. So at this point, what we're going to do is we're going to replace what used to be f of x, which was 9 from the previous video. We're going to use 2. 14 we're going to replace with 1/4. 30 with negative 1/32. 36 with 3/256. And we're going to add a fourth degree. And that fourth degree will have the derivative fourth derivative negative 215/2048 as follows. So it's going to look like this. Now we're going to have a p of x, an approximating Taylor series polynomial equals 2. And if you want, you can put it over the 0 factorial plus 1/4 times x minus 4, because we're centering it at 4, over 1 factorial plus, I should say, negative 1/32 times x minus 4 squared over 2 factorial plus 3/256 times x minus 4 cubed over 3 factorial plus negative 15, so plus negative 15 over 2048 times x minus 4 to the 4th power. So let's simplify. And by the way, just one thing to keep in mind, this is equal to f of x only at where we centered the Taylor series polynomial, which is 4. So if I plugged in a 4 for each of these, 4 minus 4 is 0. All of these higher terms drop out, and in fact, p of x would equal 2 at 4, of course, and we know that square root of 4 is 2. So that's the only place it would be equal. Everything else becomes an approximation. So when we plug in here, let me grab a new color. I'll grab green. When we plug in here a 3 and simplify, you can envision that 3 minus 4 is negative 1. Negative 1 to the 1st power is negative 1, so this going to become a minus. Negative 1 squared is a positive 1, so this remains a negative or a minus. So what's going to happen is each of these successive degrees are going to be subtracted from 2. So the result is when I plug in and begin to simplify, I get p of x at 3. Remember, we plugged in 3, so this is now 3. So really, I think what I should do is I should simply change this immediately to a 3. And that way we can keep track of where we're at with the 3. So p of 3, this equals 2 minus 1/4 minus 1 over 64 minus 3 over 1,536 minus 15 over 49,152. And when we simplify, we end up with 1.732, okay, 1167, dot, dot, dot. It actually goes out some more places. And that turns out, and I got to put the decimal point in, that turns out to be a pretty good approximation, because when I grab a calculator, all right, when I grab a calculator and I take in my calculator, I plug in the square root of 3, what I get is I'll call this P of 3 equals at the calculator. And by the way, these should really be approximations, not equals. At calculator, approximately equals 1.732050. Oh, I'll just write one more digit, then I'll put dot, dot, dot. So you can see for the square root of 3, P of 3 is a reasonably good approximation. And again, I lost my decimal point there, decimal point. Reasonably good approximation. So we can see up to the 1,000th place, they're actually equal. That's a pretty darn good approximation. And what will happen is if we use other values, let's say square root of 5, square root of 2, they will be pretty good approximations as well. The farther away we get from 4, let's say square root of, I don't know, 151, we will then begin to, our approximation will be less and less accurate. How do we improve our approximation? We simply add more degrees to the Taylor series polynomial. In subsequent videos, we'll look at how to measure how accurate our estimation is at any given value of x, and we'll take a look at, again in subsequent videos, a more formal proof built upon the techniques we've developed here. Thanks for listening, and look forward to seeing you in future videos.